Hey, check. Can the people online hear me? Thank you very much. All right, so let's continue here. So this is a very quick summary of what homogeneous equation is. Don't mix the name of this homogeneous equation with the homogeneous ODE. So the definition of homogeneous equation here is given you a first order differential equation in general format. You write this first order y prime equal to everything else on the right side, which is function of x and y. And if you can find and you can prove that the function is the same as f of lambda x and f of lambda y. Basically, you replace x, y with lambda x, lambda y. You scale them up by a constant lambda, and you're not changing this function at all. Yes. Oh, louder. Okay. Okay, this is the loudest, I think. Yeah. So that's called, this function is called homogeneous function of degree 0. So in some cases, you could have basically lambda here. You can have a lambda to the power 0 at here. So the question is, how do we solve this type of homogeneous equation right here? So let's take a look at together how to solve it. So let's look at it through an example. Here is a first order differential equation. Apparently, right? You look at this, the equation is not a linear equation. Assuming x is more than 0, absolute y is less than x. And so it's just to ensure terms underneath the square root is more than 0. Okay. That's the condition. So the more you learn, the first step is always to verify or to kind of identify what type of first order differential equation it is. So then you can use the right approach, right? In this question here, obviously, we're trying to use homogeneous. So let's verify first. Let's verify if this is the same. So what do? Yeah, you replace x with lambda x, replace y with lambda y. You can quickly actually show that, okay, so this is exactly the same as your original f of x, y. So that verification give you the next step of clue. Okay, I need to solve this question by treating it as a homogeneous equation because the function here is a homogeneous function of degree 0. So step 1, you write this function fxy. You write this function into this format, here. So basically, so this is your f of xy here. We try to transform it, but not changing it. Okay, just rewrite it into a format as a function of y over x. So how do we do that? You try, if you want to change this y to y over x, right? Then you need to divide this term with x. So what we do is we can divide both the numerator and denominator, right, with this x term. Okay, and let's see what we have. All right, so let's go back to the function f of xy. So let's rewrite it over here. So I'm gonna just basically break this fraction into 2 terms. There, right. So you already have y over x for the second term. So let's see how we treat the first term over there. To treat the first term, you move the x into the square root. So then you get x squared minus y squared over x squared plus y over x. And then the x squared minus y squared over x squared is 1 minus y over x squared plus y over x. So this is your original function f of x, y. Now it's rewritten in this new expression. It's still the same. Am I sharing the right video? Wait a sec. There we go. Technology. All right, so for the benefit of the people online here, just quickly go through this. I'm not sharing the right screen. So this is a function what we did. So we are transforming the f of x, y here into this expression in terms of y over x. So now this whole thing here, you can clearly see this is a function of y over x. As long as the function f of x, y is a homogeneous function of degree 0 or even more degree, you can always rewrite it, transform it into a function f of y over x. Okay, so you can always do that. So once you get to this step, and then formal solution is step number 2, we let u equal to y over x. And that gives you y equal to u times x. The idea, as you're going to see, is we introduce a new variable u, and then the original first order differential equation, we will be able to transform it into a function of u in terms of u variable, and which will become a linear actually. All right, so what I mean is, here is your right side expression with the definition of u. So this function is become f of u, and then the expression can be written as u. So 1 minus u squared plus u. So function f y over x can be written in terms of u now. And now, so basically your original differential equation becomes y prime, right, equal to this f of u. But what is y prime? You don't want to mix the y and the u together. So given the new definition of u, we have y equal to ux. So basically your y prime, right, based on this expression here, using product rule, y prime equal to u prime times x, then plus u times derivative x with respect to x is 1, right? So your y prime is basically u prime x plus u. So now I can rewrite this y prime equal to f of u into u prime x plus u equal to this whole f of u term, which is 1 minus u squared plus u. So the original differential equation, right? I don't see any y anymore. Now this time it's just the u here. Okay. I mean, u is defined as y over x. If y is a function of x, then u must be also a function of x. you can simplify this a little bit here so that u and u cancel here. And you're basically left with a linear first order ODE at here. So we have u prime basically is du over dx, and then times x equal to 1 minus u squared. So I think at this stage, when you look at this kind of equation, you should be able to know what approach to use to solve this kind of differential equation now. So what comes into your mind when you see this? What approach would you use, or would you be able to use to solve it? See the sign here? I think the sign means separating variables, right? Yeah. So you put all the u term together. You move around and put all the x together, put all u together, and obviously this you can separate the variables, and then you integrate both sides. So this side integration is fairly straightforward. You got ln x, so plus constant. Now this side here, I mean, you do need to probably remember some formulas. So this is basically arc sine, okay, give you that result of the derivative. All right, so finally, you solve for the u, and u equal to sine ln x plus the constant c. And that's not the end of it. Your objective is solve for the y, right? So remember what u is. U equal to y times x. So now I can substitute the u back with y times x and solve for y. So y equal to 1 over x sine ln x plus c. That's the final results of this differential equation. If you have an initial condition given, then you can substitute and solve for constant c, but otherwise, right, and you can just leave it as it is. Okay. What's that? U equal to y times x, right? Yeah, okay. All right, so any question on this? Yes. Oh, sorry, yes, of course. What am I thinking here? Excellent. Excellent. Good job. Yeah. Okay, so that is the approach to solve for a homogeneous equation. So let's let it sink in a little bit. Let's see, right? First step, of course, you have to identify it's a homogeneous type of equation. Actually, the more you do it, you'll be able to have a good feeling. You know, once you look at the expression f of x, you more or less will be able to identify that. Okay. But the first step to do that is you rewrite this f of x here, fxy here, into a function of y over x. Okay. So just manipulate, and you can rewrite it into this function of y over x, and then you let u equal to y over x. Your original first order differential equation can be transformed into a linear first order differential equation in terms of u. And you use the typical approach learned for linear first order ODE to solve for u. Once you get the u, and you get the y automatically. So that's the approach for this type of equation here. Okay. So while you're practicing from your assignments, or you look at your lecture notes, or even some reference book, at this stage, I would recommend that always examine the equation first and see if you can actually identify the type of equation quickly. Okay. All right. So now I want to add. So I said, there's 3 different additional types we're going to cover. Another type we're going to cover very quickly is called Bernoulli equation. Okay. But before we cover the Bernoulli equation, I want to cover another one here. Okay. But this one here, I would call it more of a bonus here. Okay. Yeah. So let's just call it a bonus type. And this type here is called exact equation. And you will see the connection between this exact equation and what we have learned in 248. Right? Okay. Sometimes you probably will be given a differential equation in this format. So the f of xy here, okay, is a fraction of 2 functions. So numerator is function xy, denominator is also function of y. So even though this looks very complicated, but it's still a first order ODE, right? I mean, technically, the example we did here, right, that is also in that format. You have a fraction of p of xy over q of xy. So then you can rewrite this function, this equation here, as p of xy times dx plus q of xy times dy equal to 0. So now here comes the very special kind of situation now. So I need to write it down here first. So for certain cases, now we can find a function f of xy. So basically, there might exist a function f of xy such that df equal to pxy dx plus qxy dy. So that's the very special situation. Of course, this doesn't happen all the time, but sometimes happens. So basically, if I read it again, somehow there exists a function fxy, f of xy, and remember what do we call this, df? What do we call this in 248? No? Huh? Sorry, one by one. So Berge, what did you say? Fraction? Differential. Okay, not quite. What do we call this df? It is differential, but there's a proper name for it. There's another adjective word in front of differential. Total differential. Exactly. Right? So this is a total differential because it's a function 2 variables. So essentially, I can reword it. You may be able to find a function f of xy. And if you take the total differential of that function f, and then you end up with exactly the left side of this differential equation. Okay, right. So that's just the ideal situation, right? So it really could happen. But so what if it can happen, right? If it does happen, then meaning the whole left side here becomes df equal to 0, right? So if df equal to 0, then I can solve for this f by integrating both sides. Right? So basically, let me put down here if f of x, y exists, right? So then you can do this step. So when you integrate a d anything, you get back this whatever followed by the d, right? Get back whatever followed by the d. And when you integrate a constant, what do you get? You get a constant c. Okay. So that's basically the solution, because you're looking for a solution for y, but of course now you probably want to find an implicit solution for the y. You may be finding, x squared plus 2y squared plus lowering y, whatever, equal to c, for example, right? Yeah. So that's give you basically an implicit solution, right? So the explicit, sorry, yeah, that give you an implicit solution for y. Okay, so it's just example here. So as you can see, the key at it here is, right, when you see a function like this kind of format here, the key is, do we have a function f of x, y, right? And does it exist or not? Okay. And how do we find that f of x, y? If it exists, then how do we find that? So there are basically two questions. And if you can answer these two questions, then you got a solution here, essentially. Okay. Yeah. So when this function f of y exists, okay, we call this differential equation. Okay, we call this differential equation as exact differential equation. Okay, so let me show you an example. Okay, now I'm not going to go into too much depth at it here in this class, but we will actually look at this kind of question. We have a similar question in scenario we had to cover in 248. So we'll come back to this type of things in the other course. Okay, so let's take a look at the example first. Okay, suppose you have this differential equation. So I already break it down, into p of xy times dx plus q of xy times dy. This is your p of xy. This is your q of xy. Now, without telling you how, okay, I'm going to tell you that we can find a function f of xy, and this function f of xy is x cubed y plus 1/2 x squared y squared. I can find this f of xy function. And what's so special about this? Such that you can verify. If I take partial derivative partial f, partial x, I actually get pxy. If I take partial derivative with respect to y, I actually get q of xy. Okay. So this is basically the total differential, right? The total differential here. Fx dx, Fy dy. So that means what? That means the equation given over here is an exact equation. So the whole left side can be written as df over df equal to 0. So then you integrate both sides. So you already have the f function here. So you get x cubed y plus 1/2 x squared y squared equal to a constant. And that's it. That's your solution. So you don't have a explicit solution, but you do have an implicit solution here for the y. So now I'm sure you basically asking the question here. How did you find that f of x, y, right? Yeah. So I need to leave a 2 comments here as a more or less of a question marks, but we'll be able to answer that in the other class. Okay. So 2 questions for you to think about it. Okay, just to let it sink in. We don't have to answer for now. First question is, how could we know, right? How do we know that this function fxy exists? So basically, how do you know you have a function so that its total differential actually give you this whole the whole left side of the differential equation? And the second question is, okay, assuming you know, right? So assuming if fxy exists, then how do I get that function f? You obtain the function f based on given condition. The given condition here, you have the function p, and you also have the function q. So we'll show you later, okay, if you have this p and q, and you know that based on the given p and q, you can determine, yes, this is an exact equation. And then you can actually use the appropriate approach to find this function f. So that's the 2 questions. I will leave it as a question mark at here without answering this class. We'll answer that in the other class. Okay? Yeah. So consider this is a bonus type of differential equation. In my lecture notes, I also have given you the formula as a matter of fact to find the f based on p and q. But there's always a question, basically, the first question. You have to be able to first identify, is there a function f exists or not, right? Any question on this part here? So if it's a bonus, so chances are probably not going to test you in the exam, but this actually will be part of the 248 content. All right, so now we still got time, so let's finish the 3 additional type I mentioned. Okay, so let me maybe just jog your mind here. So there's 3 additional type 1 is the what's the type 1? Separable equation. Type 2 is the homogeneous equation. So here comes the 3rd type, which is also the last type that we're going to deal with first order differential equation, is the so-called Bernoulli equation. Obviously, this type of equation named after a mathematician called Bernoulli. So let's take a look at the format of this equation and how to solve this type of differential equation. So Bernoulli equation is defined by the following type, the format: y prime plus pxy equal to qxy to the power of n. And n here is not 0, n is also not 1. So n does not take 0, does not take 1. N can take any other integer numbers. Anybody tell me actually why we're excluding n equal to 0 and n equal to 1? What happened when n equal to 0? Yes. When n equal to 0, you put an n equal to 0 here. You basically get what? This is 1, right? So then that equation becomes a linear first order ODE. If n equal to 1 here, and it's a y here, your q of x, what does it become? If n equal to 1. All the names, I want you to be able to say it because it's a language. Yes. No. Yes. Pardon me? Yes, separable. But I wanted to hear the properties. So when n equal to 1, yes, you can separate. Okay. You can certainly separate to solve it, but okay, so maybe let me write it down here and see if you. What do we call this type of equation? What's the proper name for this? When this is 0, what do we call this? Exactly, homogeneous first order ODE, right? Yeah. Okay. So that's why we're excluding n equal to 0, n equal to 1, because we already dealt with them. Okay, they're not really anything special. And only special if n is not 0, not 1, then you got a basically a nonlinear ODE, right? Because you got a y to the power n here. So what should I didn't call it homogeneous equation? I said it's homogeneous or ODE, right? Because we give the name homogeneous equation to the type 2 that we had just dealt with. So as a comment here, so Bernoulli is nonlinear. And a nonlinear equation, the trick is often you couldn't find an exact solution. That's the tricky part of nonlinear equation. So to solve a nonlinear equation, you often use analytical approach. You often use a numerical approach, okay? Like what you learned in 246. But for this Bernoulli equation here, you will find that exact solution exists. So basically, we can provide an exact solution for this type of nonlinear equation. This equation first introduced in 1695, so after 400 years, actually, we're still learning it. Okay, so the question is, how do we solve it? Okay. So here's a proper approach to solve this type of a Bernoulli equation, right? I'll write down the steps that are here. First step, divide y to the power of n by both sides of the equation. The equation, by the equation, I mean this equation here. So you divide y to the power n by both sides of the equation. So then we get y prime over y to the power n plus p of x. So you already have a y here for p of x term. So when you divide y to the power n, that becomes y to the power 1 minus n. N minus 1. And the other side is just become q of x now. And that's the first step to normalize it like this way. And then step number 2, you're going to introduce a new variable u. Let u equal to y over 1 over y to the power n minus 1. So basically, it's this term here. So you're letting u equal to that coefficient for the p of x. And this is equivalent to be written as y over y to the power of 1 minus n, right? Y to the power of 1 minus n. The objective, remember, just like that homogeneous equation, when you introduce a new variable, and your basically objective is to rewrite the original differential equation instead of using in terms of y. Now we'll rewrite it in terms of u. That's the objective. So based on the introduction of new variable u, let's take the derivative of u. But when I write the u prime at here, okay, in the background here, it's basically you're taking derivative u with respect to x. Why is the x? Because I know I have x here, right? I mean, if this is a t, then u prime means du over dt, right? So u prime, you take the derivative. So basically y to the power 1 minus n derivative. You calculate the derivative as a power term. This is 1 minus n. Y to the power 1 minus n minus 1. That becomes y to the power negative n. Chain rule, right? And then y prime. So that's your u prime. Give you this expression. So I can rewrite this side here a little bit here. So 1 minus n. This is y to the power negative n. So I can rewrite it as y prime over y to the power of n. So obviously I have a y prime over y to the power of n, which is exactly the first term in the Bernoulli equation. So I can replace this y prime over y to the power of n using the relationship over here. So what's the relationship? So y prime to the power y over n equal to u prime, right, over 1 minus n. So then now this original Bernoulli becomes u prime 1 minus n plus px times u and qx. Thus, simple introduction of the variable u has transformed the original differential equation from in terms of y, now in terms of u. And what's even better is, now you look at this new differential equation. This is linear. So I can multiply the u 1 minus n to normalize it. So now you got a linear first order ODE. So it's a linear, meaning, and this is not a homogeneous here, you have a non-zero term. So then I can apply which approach to solve this? Exactly, right? Integrating factor method to solve this. So now you can apply the integrating factor approach. Good. So that the key here, right? You look at the key for Bernoulli equation, of course. First, you had to be able to identify the Bernoulli equation. The key is to introduce the variable u. So your u has to be introduced like this, cannot be anything else, otherwise it won't work. So what I'll give you an application here, and then we can take a look at the example. So let's just suppose you fire bullets with an initial velocity of v. So aiming at a certain object. So once you fire the bullets, we all know the bullet was subject to resistance force. So I'm not sure what this object is, but the resistance force, okay, to the bullet, it can be written as lambda1 times v plus lambda2 v squared. So the faster, basically the faster the bullet velocity is, the more resistance force it will experience. So the object could be meat, it could be something else, but somehow the resistance force is this relationship. So if you are required to calculate the velocity or the position or the motion of the bullets, so then what do? We can use Newton's second law, okay, to construct a differential equation out of here. So assuming this is the only external force, okay, applied to the bullet, and the bullet has a mass of m, right? This is basically the only thing you have. So m, okay, dv over dt. X is position. So x double dot is acceleration. So dv over dt is acceleration. That equal to lambda 1 v lambda 2 v squared. Just write it just slightly different. So m dv over dt minus lambda 1 v equal to lambda 2 v squared. Now this final product of the differential equation here exactly conforms to the Bernoulli equation, right? And this n here, this 2 here, so basically n equal to 2. Okay? If you look at the general format of Bernoulli, if you let n equal to 2, right, that's basically what happens here. But I'll give you an example how the Bernoulli's equations can be seen in a real example here. Okay. All right, so now let's look at how we can solve this one using an example. So we more or less talked about how to solve, but this is a very general approach. So let's apply this approach to a specific example here. So y prime equal to ay minus by squared. A and the b are constants. Okay, so this question is actually relatively simple because A and B are constant. If I look at my original general equation for the Bernoulli, the one in front of the y, the one in front of y power n, they're a function of x. But now in this example, they're constants, right? So they're actually relatively simple. So if you're not too sure, you can write it in this way. Then you can clearly see, now this is a Bernoulli with n equal to 2. Now, before I apply the approach to solve this Bernoulli equation, I want to see, anybody actually think of a different way to solve this? Actually, maybe easier to solve it using the Bernoulli's, the approach to solve Bernoulli here. What would be an alternative way to solve this one here? Maybe easier, maybe not. Anybody? I mean, it's nonlinear, right? Let's think about all the types that we have learned. Which type could you fit this into? Yes. I don't think I can make it homogeneous. You're trying to take the y out like this, and then what? Divided by y, like this. Well, it's still not homogeneous, right? It's still not linear, still non-linear. Sorry, come again? How would you do that? How about this? So y is dy over dx. Huh? That's assuming y is function of x. How about move all the y terms like this? Can I do that, right? So what do we call this approach again? Separating variables, right? So now you might wonder, how am I going to integrate this side here? Yeah, there's a technique to integrate depending on the a and b value. So you can factor the bottom here out as a minus by. So if you recall, when you have a integration like in this format, it's a fraction. The bottom are multiplication of two factors. There's a technique called what's the proper name of that? Geez. It basically you what's it called, a power factor methods? You basically you expand the two terms into two fractions, right? Does that look familiar to you, right? So when you have a fraction here, you can break it down into an addition of two terms. And you can find the a and b using some formulas. A and b are constant based on the actual small a and b. Okay. Then the integration of each one of the term will be much simpler, right? To become a log term. So that basically is an alternative approach. When you say this, you don't really have to apply what we have shown in terms of Bernoulli. Okay. So, but in the next lecture, I'm going to follow here to actually use the Bernoulli's approach, okay, to solve that equation. All right, any questions? Feel free to come over. See you. Thank you. Sorry, just